So I want to look at this next sum just to give us a quick review of what we did yesterday. So remember, K is our index here. It is showing where we start. N is going to stay the same. So N is going to be in all of our terms. K is going to get replaced with our 1, 2, 3, and so on. So this is going to look like 1 over N times 1 squared plus 1 plus 1 over N times, well, now we're going to put 2 in for K, plus now we're going to put 3 in for K, all the way up to putting in N for K. So the term before this would be N minus 1. So it look like 1 over N times N minus 1 quantity squared plus 1. So that's how this sum would look. And why are we talking about these sums? Well, you'll see in just a minute. Because we left off yesterday, the last thing that I said was we wanted to approximate this area. And we wanted to think about how best to do that. And so the easiest way to do this, we talked about how when we were approximating a derivative, we were doing it in terms of slope. And we used it with a slope formula that we already knew how to do. And so if we're trying to find an area here, well, we don't know how to find the area underneath our curve. That's not something we have a formula for. But we do have a formula for area of things with straight lines. So what we're going to do is we are going to subdivide this into chunks. So let's say these chunks. And we're going to use the area of a shape that we already know how to find the area of, which is going to be a rectangle. So we're going to use rectangles. And the reason we're going to do this is because we already know how to find the area of a rectangle. The area of a rectangle is base times height. Length times width for some of you, but base times height is another way to write it. So we can create these rectangles, and they're going to be pretty close to the actual area underneath the curve. Now, this isn't perfect, just like our slope method by picking a point very close wasn't completely perfect. Right? There's some of this area up at the top that is left over. There's this little sliver of area that isn't covered. So we will have things like that where there will be inaccuracies, but this can help us give an approximation. And so these rectangles can help put it in terms of an area that we already know how to find. That's going to be the idea here. And so we're going to use this base times height for each rectangle, and we are going to add them up. So our base is our difference in the x-coordinate. That is our change in x, or delta x. Delta is used to say a change. And our height x distance here for the base. And then the height is going to be our y coordinate. Y coordinate. Usually we use f of x to stand for the y coordinate. And we are going to add these together for each of our rectangles that we have. And so that leads to this formula. This method of adding together the rectangles is going to look like this last summation formula that we have. That's why we spent yesterday talking about this notation, because we use this notation when we talk about finding this area. Now, there are two different choices that we can make for how we build these rectangles. Approximate by building rectangles. So for a left-handed versus right-handed, what that means is that, let's say we're going from 0 up to this point over here. If we are using left-handed rectangles, then what that's going to mean is that we are always, as a rule of thumb, so we'll go 1, 2, 3. As a rule of thumb, we are going to always use, when we talk about our height, we're going to use the left endpoint. We're going to use the left endpoint. So we are going to start with that left endpoint and build that as our height for each of our rectangles. So this will create the first rectangle. So between, for the second rectangle, we're going from this point to this point, from 1 to 2. And so when we're making that choice for which to use for our height, we're going to use the one on the left, which will create this rectangle. And finally, from 2 to 3, when we're making the choice between them, we choose the one on the left. And so we're going to go up to this height for the third rectangle. Now, if we were to do this with a right-handed rectangle, then our height is going to be the right endpoint. So again, we're going from here to here. And I'm going to mark off again. We'll call this 1, 2, and 3. This time, when I'm looking at my space from 0 to 1, if we're doing it the right-handed way, when I make the choice between the two, I'm going to choose the right endpoint. So between 0 and 1, I'm going to choose 1. And build my rectangle from there. And then from 1 to 2, when I make the choice between which point to use for the height, I'm going to use the one on the right. So I'm going to go up to here. Last one, between 2 and 3, when I make the choice of which one to use, I'm going to pick the one on the right, which is 3. So I'm going to go up to this height. And you can see how these two answers can give us slightly different answers for the area. Because of which endpoint we are picking. And these are called the left-handed. Since these are called Riemann sums. This is named after a mathematician. And it's going to be called RAM for short, RAM. The left-handed rectangles, if we use the left endpoint as our choice for all of them, that's going to be called LRAM, or a left Riemann sum. And if we choose all the points on the right, this is going to be called RRAM, or a right Riemann sum. And the hypothetical idea here is we can make our approximation more accurate by using more rectangles. Just like with our slope for the derivative, we hypothetically chose a point that was really close to the point I wanted to find the slope at, and the closer and closer I got, the more and more accurate that our measurement got. So, for example, if I added in more rectangles here, and instead of going every 1 unit, I went every 0.1 unit and started building rectangles that way. There's less dead space to be covered. And so these rectangles are still not quite accurate, but they're going to get us much closer to the answer than our wider intervals are. So the hypothetical way to do this is if I had hypothetical my trick to this would be if I had the base, because that's the length that I'm changing here, my width of the base would be infinitely small, right? If I just had this small sliver of the rectangles, then I'd basically just be drawing the area of the curve. And so here comes our old pal, the limit again. And so when we go to define the integral, it's going to be a limit of this sum if I let my rectangles be infinitely tiny. And I'll show kind of a visual tomorrow of what that's going to look like. But for now, let's do some examples with building this rectangle. This is where you want to write Riemann sum. Riemann sum. And then I'll come back to this one. But let's do an example. We're going to do a left Riemann sum and a right Riemann sum. So f of x equals 16 minus x squared. And we are interested in the area from 1 to 3. So let's go ahead and draw this picture. Let's see. I know that 1, 2, 3, 4. One thing I know is that, let's see, our vertex is at 0. and it crosses the x-axis at 4. So our graph looks like this. And so I want to find the area underneath the curve from 1 to 3. Starting at 1, going to 3. And we are going to use 4 equal subintervals. What that means is that I'm going to be building 4 rectangles. So let's start with our right Riemann sum. And the way we're going to write this is R ram for right Riemann sum. And then we're going to use a little 4 down here to say that we're using 4 rectangles. So there should be 4 terms here that we're going to add together, one for the area of each rectangle. So let me show you how this is going to look. Right Riemann sum means that, well, I have 4 rectangles here. Well, 4 rectangles means that I need to go between 1 and 3 and build 4 rectangles. So that means each rectangle is going to have a base that is equal to 1/2. So I have one from 1 to 1.5, and then from 1.5 to 2, 2 to 2.5, and 2.5 to 3. Those are my 4 rectangles. And so let's mark off our 4 points. And if I'm choosing which point to use as my height, remember my height for a right Riemann sum is going to be the right endpoint. So I'm going to start by choosing my rightmost endpoint. And that's going to be my first rectangle. Then between 1.5 and 2, 1.5 and 2, if I'm choosing between the two, I'm going to use the rightmost endpoint. So I'm going to choose 2 as my height. Between 2 and 2.5, if I'm making the choice, I'm going to choose the rightmost endpoint. So I'm going to choose 2.5. Between 2.5 and 3, if I have a choice, I'm going to choose the rightmost endpoint. So I'm going to choose 3. And so those are my 4 rectangles. So each rectangle has an area base times height. So our base is always 1/2 for each of these. That's our kind of width of the x-coordinate. Times our height here. Remember, we chose our rightmost endpoint. So we chose 1.5 for our first rectangle. So f of 3/2 plus our base here is 1/2 times we chose the rightmost endpoint here. So that was 2 plus 1/2 is our base times our height. We chose as the rightmost endpoint. So that was 2.5. And we're saying f of 5/2 because we want the y coordinate here. Plus our base is 1/2 times our height. We want to be f of our rightmost endpoint here was 3. So this is the sum that we would work to calculate. So we would go 1/2 times f of 3/2. Well, 3/2 squared is going to be 9/4. So let's see. This is 64/4 minus 9/4. So this is 55/4. F of 2 is easier. This is 16 minus 4 is 12. Plus, and then a whole bunch of arithmetic. All right, last thing I want to do before we go. I want to do the left Riemann sum. I want to set that up. I at least want to give you the diagram. And then from there, I want to see if you can write it out. So same diagram, same area, but we're going to do something slightly different to approximate it. This time, when in doubt, I'm going to choose the leftmost endpoint. So I'm still going to go from, I'm still going to go from 1 to 1.5. But this time, when I'm choosing between 1 to 1.5, which one to use for my height, I'm going to use the leftmost endpoint. And so this is going to be my rectangle. Between 1.5 and 1, if I have the choice between the two, I'm going to choose the leftmost endpoint, which is 1.5. Between 2 and 2.5, if I'm going to make the choice, I'm going to choose the leftmost endpoint. Between 2.5 and 3, if I have the choice, I'm going to choose the leftmost endpoint. And then write out this sum. So I'd like for you to try and do that and write out that sum and figure out what it's going to be. And we'll have a general rule for this going forward.